Okay, good afternoon. Let's go ahead and get started. So today we're going to be talking about this notion of continuity of functions, one-sided limits, and infinite limits. And beginning with continuity, we should recall that most of the functions that you've seen in your previous courses, like pre-cal or algebra, most of these functions are what you could say are well-behaved. They're kind of nice, smooth-looking functions, and the reason why you see so many of these smooth, nice-looking functions in these courses is that they're easy to deal with, and the properties of them are easy to define. And these are typically examples of what are known as continuous functions. So first, I'm going to give a definition of continuity, and then we'll discuss the different types of ways a function cannot be continuous. So this is the definition. So a function f is continuous at a point C whenever the following conditions hold. So all of the following conditions need to hold in order for a function to be continuous at a point C. So number one, f evaluated at C is defined. Number two, the limit as x approaches C of f of x exists. And number three, the limit as x approaches C of f of x is actually equal to the function evaluated at C. If these three properties hold, then we say that the function is continuous at x equals C. Okay, so let's look at some possibilities here. So suppose that we have some interval AB, and suppose C is right there. We could have a function maybe look like this. Okay, this is one example. Hopefully you can see that there's a little hole right there at x is equal to C. So here we see that, so if this is the graph of our function f of x over this interval, we see that indeed the limit does exist, right? The limit as x approaches C of that function, say it's L, it does indeed equal L. But f of C does not exist. So this function here is not continuous at x equals C. Because the function is not defined there, right? It has to, in order to be continuous at a point, all three of these properties need to hold. So this would not be continuous at x equals C. So what's another possibility? What about, say, something that looks like this? we have some open interval AB, and then here's C. So in this case here, f of C is defined. So this exists, right? It's just simply that value right there. But the limit as x approaches C does not exist here. Okay. Now, why does it not exist? Well, if we look at the limit approaching C from the left-hand side, it approaches f of C, right? But if we look at the limit from the right-hand side, as x approaches C, it's going to be whatever value that is right there. So since these values don't match up, the limit's not going to exist. So here again, we need that limit to exist in order for this function to be continuous at that point C. So again, f of x is not continuous at x is equal to C. And then maybe I'll do one more picture here. So suppose we have something like some picture like this. So this is a third possibility for a function not to be continuous. So here we see that f of C is defined. So f of C exists. And then also the limit as x approaches C from the left and right is going to be whatever this value is. Right? We see that that limit does exist as well. So those two properties hold, but the limit does not equal the function evaluated at C. So again, we would say that the function is not continuous at x equal to C. So these are the three ways that the function will break down and not be continuous at a point. Notice now that some of these, like this right here, if we filled in that point and said that the function exists right there, then this would be continuous at that point, x equals C, for this graph here. So this is what's called a removable discontinuity. It's just one point where the function doesn't exist at that one point, and that's the reason why it's not continuous at that point C. So that's a removable discontinuity. This is not a removable discontinuity. This is what's called a jump discontinuity. There's no way to place in a value that's going to connect that graph. So you can think of continuous functions as smooth, graphs of continuous functions as smooth graphs. There's no holes. But so far, we've only defined continuity at a point. Continuous at a point, right? So now that we understand how things can break down for continuity at a point, we can say something further about functions being continuous over an interval. So this is like a continuation of that definition. A function f is continuous on an open interval AB if f is continuous at all points x with a strictly less than x, strictly less than b. So this is what it means to be continuous on an open interval. If it's continuous at every point in that interval, then it's said to be continuous on that interval. Okay? So what will these look like? There's A, B, there's an open interval there. And the function is generally going to just be something like that, at least in that open interval. Okay. So in this case here, we'd say that the graph of this function represents a continuous function on that open interval AB. Now we can verify that just by looking at the picture. If you pick any value in this open interval, say C, right, anywhere in that open interval, the function is going to exist at that point. And if we look at the limit as x goes to c, it's going to also converge to that point f of c. Okay. So this is how we define continuity on an open interval, with these three properties. Okay. Now, in order to define continuity of a function on a closed interval, we need to introduce two notions. So again, make sure you have these in your notes. F of c is defined, limit as x goes to c is defined, and the limit as x goes to c matches up with f of c. Okay, that's definition continuity at a point. And if you have an open interval and it's continuous at every point in that open interval, then it's the function is just said to be continuous on that open interval. Okay, so next definition. So limit as x approaches c plus f of x is the limit of f of x as x approaches c from the right. And limit of x as x approaches c with a minus sign is the limit of f of x as x approaches c from the left. Okay. So, and we've discussed these notions in the previous lecture, right? Looking at where the function goes as we approach the c from the left and the right. So we can distinguish those two values because sometimes they're not going to match up. Okay. So let's look at the left and right hand side limits of the following function. So f of x equals 2. It's double bar notation x. And what is this? This is the greatest integer. So integer is a positive or negative whole number. So this is the greatest integer n such that n is less than or equal to x. Okay, it's a special type of function. So let's go ahead and see what the graph of this function looks like. Okay, so let's just pick, for example, when x is equal to 1, what's the largest integer that's less than or equal to 1? Well, it's just 1, right? So when x is equal to 1, that function's value is 1. What about when x is equal to 1/2? What's that function's value?
Half.
But 1/2 isn't an integer.
Oh, so 0?
Right, you want the largest integer that's less than or equal to 1/2, right? So for 1/2, it would be 0, right? What about 3/4? It's the largest integer less than or equal to 3/4.
Still 0?
0, right? In fact, we put an open circle there. And maybe so So can y'all make that out? Let me see. Yeah. Okay. So what about when x is equal to 4/3, a little bit bigger than 1? What's the largest integer less than or equal to 4/3?
1.
1, right? So in fact, everything to this side with the exclusion of 2 is going to be like that. And then this pattern is going to continue. So then and that's what the function is going to look like. You just piece this together step by step, you'll get a step function actually. Okay? So then let's consider the following limits. So what's the right-hand side limit of this function here. As x goes to 0. This is the right-hand side as x goes to 0. So we're going that way, right? So we're starting over here and heading. So what's this limit going to be?
1.
So we're heading this way.
Or 0.
Yeah.
And then so, okay, I got it.
Okay. So what about this? What about the limit as x approaches 0 from the left? So now we're on this side and we're going this way, right? What is it approaching?
It's
Negative 1?
Yeah, it looks like it's going to go to -1, right? So here, notice that the left and right-hand side limits do not match up, right? So there's an important theorem to note. Theorem. The limit as x approaches c, f of x equals L, if and only if the left and right-hand side limits equal each other. So from the right equals the limit from the left. And both of those equal L. So if the limit exists and it's equal to L, then the left and right-hand side limits also equal L. And then conversely, if the right-hand side limit equals the left-hand side limit equals L, then the limit as x approaches c of the original function equals L. So this is a nice way to look at a picture and determine if that limit exists, right? You just look from the left and the right. We've already been doing this. If they coincide with each other, then the limit exists. That limiting value is the answer to the problem, I suppose. Okay. Okay. So now that we have this definition of left and right-hand side limits, and we see how it relates to the limit, the general limit, we can now look at defining continuity on a closed interval. So, definition. So, a function f is continuous on the closed interval AB if f is continuous on the open interval AB and the limit as x approaches a from the right-hand side of f equals f of a, and the limit as x approaches b from the left of f of x is equal to f of b. So this is continuity on a closed interval. So, for example, I guess I'll make some more room. Maybe the function f of x equals to the square root of 1 minus x squared is continuous on the closed interval -1 to 1. Does anyone know what that function looks like? Do you remember the equation of a circle? Right, so like x squared plus y squared is equal to the radius of the circle squared. Y'all seen that before? Well, if your radius is just 1, then if you solve for y, you get y is equal to plus or minus 1 minus x squared. So if that's a circle, the plus and the minus of this are half circles. So the graph of this function looks like this. On that closed interval, it's just, so here's like 1, here's -1. If I drew the whole circle, it would correspond to this equation. But since I'm limiting between -1 and 1, and we're just looking at the positive of this, then it's that half circle. Okay. So let's argue why this function is continuous on that closed interval -1 to 1. So first we need to show that it's, so first we need to show f is continuous on the open interval -1, 1. That's the first thing we need to do. Okay. So in order to do this, notice that, so if x is in, so if -1 less than x less than +1, then 1 minus x squared is greater than 0. Right? If we pick an x between -1 and +1 and we square it, it's surely less than 1. So then 1 minus x squared would be greater than 0. So the inside of that radical is going to be positive. And from a previous lecture, we know that if we have the square root of a positive number, we can evaluate the limit by just plugging in the value c, right? So then, so if -1 less than c less than 1, the limit as x approaches c of this is just equal to the square root of 1 minus c squared. We just plug in the value, right? We know that we can do that by a previous lecture. But what is this? This is the same thing as saying f of c. So anywhere inside the open interval -1 to 1, we know that we're taking the square root of a positive number, which means that we can just plug in c for the limiting value. You just plug it in. But that's the same thing as writing f of c. So we see that anywhere in the open interval, f of c is going to equal the limit as x approaches c. So that's telling us that it is continuous on that open interval. Right? Anywhere we pick on that open interval, the limiting value is going to equal the function evaluated at that point. Okay? So next, we need to show that the right-hand side limit as x approaches a of f is equal to f of a. Well, we see that, so part 2, I guess, f of -1, that's like our a in the closed interval, is equal to 0. And if we look at where the function is going as x approaches -1 from the right, it also goes to 0. And in part 3, if we look at the right-hand side limit, so f of f of 1 is equal to 0. But if we approach 1 from the left, the limiting value is going to 0 as well. So these 3 observations together show that this function here is continuous on that closed interval, -1 to 1. Okay. All right. Sort of makes sense. Do you have an image of what continuous functions look like now? There can't be any jumps. There can't be any breaks in the function. The graphs of continuous functions are going to be smooth, right? Connected, smooth functions, smoothish functions. So for example, one that wouldn't be smooth but is continuous is the absolute value. That's what the absolute value looks like. That has a sharp point, but it's still continuous at that point, right? As x goes to 0 from the right-hand side, the function goes to 0. From the left-hand side, the function also goes to 0. So the limit as x goes to 0 of the absolute value function is 0. And if you evaluate the function at x equals 0, it's also 0. Those match up, so it's continuous at that point and it's continuous everywhere else. So that is a continuous function as well, even though it has a sharp point. But there's no jumps, there's no holes in the graph. You can still more or less draw the graph of that function without lifting up your pen. If you can do that, that's a visual way of saying that the function is continuous on an interval. If you can draw it without lifting up your pen, more or less that means it's continuous. Okay, so there are properties that you should know. This is the theorem. So if B is a real number, and F and G are continuous at the point C, then following functions are continuous. So 1, B times F, 2, F plus or minus G, or by the way, are continuous at C, at the point C. So the constant times F is continuous. The addition or subtraction of the functions is continuous at that point. The product of the functions are continuous at that point, or is continuous at that point. And for F divided by G is continuous at C, provided G of C is non-zero. Okay. So now this gives us a way of thinking about a vast variety of types of continuous functions, right? So for example, think back to the previous section on polynomials. So we know that the limit as x approaches c of a polynomial function, you can evaluate that limit by just plugging in the value c, right? So this tells us that polynomials are continuous. Right? But then that also tells us that, say, rational functions are just ratios of polynomials, right? So since polynomials are continuous by this observation here, we know that the ratio of polynomials are continuous at every point that you provided the denominator is non-zero. Provided so I say we're talking about continuity on a point, at a point, so I should really say provided g of c is not equal to 0. So I'm talking about these functions being continuous at a point c. Now, if they're continuous at all points in a given interval, then these are also said to be continuous on those intervals. Okay. All right. So next, I guess I can fit it right here. Let's see. So it's another theorem. So if G is continuous at C, and F is continuous at G of C, then the composite function is continuous at C. So then F composed with G is continuous at C. So then we can start taking compositions of continuous functions and get more families of continuous functions. So for example, we have polynomials are continuous, and we know that square roots are continuous provided the value that you're evaluating it out is positive. So then we can take square roots of polynomials provided we're not taking a negative square root, and then that function is also going to be continuous. And you can get all kinds of very interesting graphs from taking compositions of compositions of compositions of functions. But if we know that each composition is going to be a continuous on a continuous on a continuous, then we know that those graphs are going to be somewhat well behaved. There's going to be no holes, no jumps. No matter how complicated looking the function is, if we know that the continuity is being stacked on each other by way of compositions or additions or multiplications or divisions, we can somewhat guarantee that the function is going to be well behaved. Not somewhat, we can guarantee that the function is going to be well behaved. Now, what do I mean by well behaved, by the way? Like I keep on saying that maybe you have like a general sense of like the function looks nice. There's nothing odd about it, right? Well, when it comes to designing algorithms, you sometimes need specific properties to help you in your algorithmic search for something, right? In particular, maybe we can illustrate this concept with the following, what I would consider a very important theorem. And this is called the intermediate value theorem. So intermediate value theorem. Anytime a theorem has a name, you should probably take your time to understand it after lecture the best you can. So, I love this theorem because it just makes sense once you understand the technical wording that it's saying. So it says that, okay, so if f is continuous on the closed interval AB, and f of A is not equal f of B, then there exists, well, let me see if I can just model the language from the book the best I can. I'm going to alter what the book says. So then, for every value k, for every value k with f of a less than k less than f of b, I should say, or f of b less than k less than f of a. So it could be that if f of a is less than f of b, then we're in this case. If f of b is less than f of a, we're in this case. So for every value k that exists in between f of a and f of b, there exists C with A less than C less than B and f of C equals to k. Let's take a moment to write that down. I'm going to draw a picture to help us understand it. Okay, so let's talk about why this theorem makes sense. We're not going to prove it, but let's at least like justify why it makes sense. So let's suppose that f of a doesn't equal f of b. Let's suppose that f is continuous on the closed interval ab. And okay, so that's what we're going to assume first. So here's a, here's b. Okay, and we're supposing that f of a doesn't equal f of b. So let's assume that f of a is smaller than f of b. If one of the two possibilities is going to hold. Either f of a is smaller than f of b, or f of b is smaller than f of a. But let's just assume for now that f of a is smaller than f of b. So we're looking at the graph of this continuous function. There's f of a, and then maybe like here's f of b. Okay. Now, what is this saying? It's saying for every value k in between f of a and f of b, there is a value c in this interval that the function will map c to k. So let's just pick some arbitrary k in between f of a and f of b. So that's a k that's squeezed in between them, right? Now we know this function is going to be continuous. We're assuming that this function is continuous in the closed interval ab. So if we draw the graph of this function, we're going to connect this point with this point, right? And when we connect those points, can we ever jump? Can the graph ever jump? No, right? Because it's continuous. Does it have any holes in it? No, it's continuous. So how am I going to get there? Well, it can do all kinds of things, like that, maybe. But look. There's my c. If I look at f of c, it's equal to k. And it's because the function is continuous on that closed interval. We can't ever jump over and not include k if we're going to connect from there to there. Does that make sense pictorially? You see that? So no matter what number anything we've taken between that interval like there, well, there's something that'll be mapped to that number no matter what. And it's because the function is continuous on that closed interval. Now this gives us something to work with. This gives us something to work with. Well, you're probably confused as to what. So let me just go ahead and say that finding the roots of a function, finding where a function is equal to 0, is a very important thing to do. In terms of optimization, maybe finding a 0 corresponds with a minimum, a local minimum or local maximum, or something like this. Finding zeros of a function is just in general important. This theorem, this intermediate value theorem, helps us find zeros. Well, how? Maybe something like this. Let's just pose a question. The question: does f of x equals to x cubed plus 2x minus 1 have a 0 in the closed interval 0, 1? Does it? So we're not going to explicitly find the 0. We're just going to know if there's a 0. If there's a value of x in this interval that makes f of x equal to 0. And we can use the intermediate value theorem to tell us. And the answer is yes. How do we know? What's f of 0? It's minus 1. What's f of 1? So it's 1 plus 2, so it's 3 minus 2. I mean, minus 1. It's 2. Right? So we know that this is telling us that f of 0 is not equal f of 1. Right? Also, this function f, it's a polynomial, so it's continuous. On the closed interval 0, 1. Okay? So since f of 0 is strictly less than 0, which is strictly less than f of 1, the above observations, it says observations over there, the above observations together with the intermediate value theorem imply there is a C with 0 less than C less than 1 and f of C equals 0. So the intermediate value theorem tells us that there must exist one value in that interval that has x equals, f of x equals 0. So this is where having knowledge about the continuity of our function tells us the existence of something that we couldn't obviously see. Like notice we didn't even graph this thing, right? If we had a picture of it, then yeah, we could probably see if it had a 0. But a lot of the functions that you encounter, you don't have a picture of it, right? But then you can use nice properties of continuity if you know that it's continuous to infer properties about the function. What's more, you could probably devise an algorithm based off of this observation to find the 0 or get close to the 0. So we know that it exists now. How could we find it? So let's talk about that, because this is something that as data scientists you will end up doing, is devising methods and techniques to find properties of functions or values that give functions a certain thing. In this case, we want a 0. So we know something by this observation. We know there is a 0 of this function in there somewhere, right? So we know if we're going to try to find that 0, we just need to search inside of there. So here's 0, here's 1. It's somewhere in there. In fact, I'm going to draw it a little bit. Somewhere in there is our 0, and we got to find it somehow. So what we can do is we can take the midpoint of this interval, and maybe I'll illustrate it. By the way, the midpoint of two numbers on a line is just a plus b over 2, right? So in this case, it's going to be 1/2 is the midpoint. 1/2. So then let's look to the, so what is f of 1/2, by the way? That's going to be 1/2 cubed plus 2 times 1/2 minus 1. So what is that? 1/8 plus 1 minus 1. So it's just an 8. So 1/2, the midpoint is not our 0. Okay. So let's look to the left and the right of this midpoint. Okay. Well, actually, we don't have to. We know something. F of 0 is -1, right? So notice, so f of 0 is -1. F of 1/2 is positive 1/8, right? So the intermediate value theorem now says that we don't have to look all here. We can just look in there. The function is continuous between 0 and 1/2. It's negative at f of 0, and it's positive at f of 1/2. So if it's continuous in that interval, and this evaluating function here is negative, evaluating the function there is positive, then somewhere in there we have to cross f of c equals to 0. So then we take the midpoint here. So what's f of a 4? What is that? So this leaves us 16 times 4, so 40 plus 24, so let's leave 1/64 plus 1/2 minus 1. So what does this become? So this would be, so if I combine these ratios here, what is it going to be? So multiply this by 32 over 32, so we get 33/64 minus 1. Right? Did I do that right? If I combine those. If I had a calculator, I'd just like put in the decimal approximations. I don't have a calculator on me, so I'm just doing it like that. So this is going to be 33 minus 64 over 64. Oh, this is negative. I can just see that this is negative, right? So now I know that, so at a fourth, f is negative there, f is positive there. So now what interval do I need to look at? That interval, right? And the intermediate value theorem, again, because the function is continuous, tells me that there is some value in there where the function is going to equal 0. So then I do it again. I take the midpoint there. So I know that f of that's positive, f of that's negative. So what's the midpoint now? It's 1/4 half over 2. That's my new midpoint. What is that? 3/4 over 2. Right?
Yeah. 3/8, right?
Yeah. So 3/8. Okay. So then, what's f of 3/8? Does someone have a calculator that they can do that for me really fast? Just that function at 3/8. Anybody?
Yeah, I can pull it up just one sec.
I got a decimal value if that works.
Yeah, that's fine. Is it positive or negative?
Yeah, it's negative 0.197.
Oh, look, this is kind of getting close to 0, right? But it's negative. So now the new interval is here. It's somewhere in there. And the intermediate value theorem again says the 0 is going to be in there. So then you take the midpoint here. And if you still have your calculator out, let's see if we can do this real fast. So at 3/8, it was negative 0.1 something, right? So now 3/8 is a half over 2. So what is that? 7/8 over 2, so 7/16. So now what's f of 7/16? If you have your calculator out still.
I got negative 0.04.
Hey, that's good enough for me. Right? That's good enough for me. So what are we doing? This is like an iterative method, right? Where we have a midpoint and then we update. We have a midpoint, we update. And at each time in the back of our minds, what are we thinking? Intermediate value theorem says that zero has to be in the next interval. You keep one side negative, one side positive, and you just keep on bouncing, making new intervals until you decide you're good enough. So this actually has a name. So this is called the bisection method. And it's a way of finding zeros of continuous functions on a closed interval when you know that negative on one side, positive on one side, or positive on one side and negative on the other side. So I think that will be it for today's lecture. Okay. Now, I'll go ahead and stop the recording now.